to the video about properties of logarithms. Let's get started. To begin, let's talk about how you're going to add two different logarithms. Just like with exponential functions, you have to make sure that the logs have the same base. Notice that these are both base n, and if that is the case, you can combine into a single logarithm, keeping that base, but then taking the product of the two logs arguments. So here we have the log base n of a times b. Let's do some examples. So for the first example, the direction should say to evaluate. So if you looked at the first log, you wouldn't know how to evaluate log base 2 of 3 exactly without a calculator. But let's use our log property. We can add these two logs because they have the same base. That would be log base 2 of 3 times 32 over 3. Oh, and then those 3's would cancel, and we would get log base 2 of 32. So now the question is, what exponent do I put on 2 to get 32? Oh, the answer is 5. So I was able to evaluate this by adding the logs together, although individually I wouldn't have been able to do that. This example over here, I just want to combine these two logs. I can't actually give this a value since the arguments have variables. So our log property says that when we are adding logs, we can do so if they have a common base. So we'll keep that as log base 5. But we're going to multiply the arguments. So in this case, we would get 3x cubed. And there's nothing else we could do with that. Moving on to our next property. To subtract two logs, as long as they have the same base, we are going to combine that into a single log, but this time we're going to divide those arguments. So here are two examples. In the first example, I would like to evaluate this expression. So log base 3, excellent. They both have the same base. These two logs are being subtracted, which means that this would really become log base 3 of 162 over 2. Great. And then log base 3 of, what would this simplify into? 81. And log base 3 of 81 is 4, because 4 is the power. You'd put on 3, and you'd get an 81. The next example, we're going to combine, because just like in our previous property, we had variables in the arguments, so we can't actually find values here, but we can combine. These are both log base 10, which I don't need to write down, so I'm just going to write log. And this is going to be x squared minus 9 over x plus 3. Now, I can actually do some division here since x squared minus 9 is factorable, and it factors into x minus 3x plus 3. And now we have a factor that's going to be eliminated. This is now simplified into the log of x minus 3. Now, typically, we would say that negative 3 can't be part of the domain of this, but that can't happen anyway because that would make our argument negative. So we would just leave this as the answer. We have one more property. This property is actually a little strange. So when you have a log and it's being multiplied by something, we're going to call it m, you can do something where the coefficient can become an exponent of the argument. But the problem with this property is that it doesn't go in both directions. It can, but it doesn't work for everything. So I'm only going to say that this is an arrow, not an equal sign. So if it starts out in this format, we can turn it into log base n of a to the m power. So here's some examples of why you might want to do that, because that seems kind of a weird thing to do. Our first example, notice that we have two logs that are being added. They're the same base, but you can't add these two logs with this having a coefficient in front. That's not part of the property. So here's a really good reason why we'd want to move this to be an exponent, because now that coefficient is no longer an issue. And now I can combine these two logs together like that. So, sorry, I forgot to put the directions here. The direction here would be to combine, same for over here. So I only like to move the coefficient up to be an exponent when there's a reason to do it. And the reason here is because I want to combine these two logs, and I can't do that when there are coefficients in front. So here we go. We have a coefficient in front. These are two logs that have the same base. ln actually is log with a base of e. Probably have talked about that in class already. May not have gotten to it, just so we have that there. So these can be combined, but before I combine them, we definitely want to move that 4 up to be an exponent on x. And now this would be ln of x cubed over x to the 4th, which simplifies to ln of 1 over x. Now, I did specify that this rule only works in this direction. It does work in the other direction, but not for every situation. So I'm going to give you an example. Would 2 log x equal log of x squared? I always like to think about equality of things having the same exact graph. So I graphed 2 log x. And I got a nice looking log graph, asymptotes at x equals 0. Nothing too funky there. And then I graphed log of x squared, and you can tell they are not the same graph. However, you'll notice that this blue graph has the exact same piece on the right-hand side that would match this red graph over here. It's that this graph has extra points on it, right? So these are sometimes equal, right? That's the correct answer to this question. Do these equal? Sometimes, right? It would be equal when x is greater than 0. Okay, but because it doesn't always equal, that's why this property is very dangerous if we ever went from exponent to coefficient, right? There's no reason to do that. That would actually have you lose parts of the graph, right? If we move this 2 up to be an exponent, we're going to gain parts to a graph. And foreshadowing here, that's where extraneous solutions are going to show up again. I know it's shown up in units before. It's going to show up again. All right, that covers log properties. We'll see you in class.